So the goal for the day is pretty straightforward. We're simply going to go through the practice exam and see how we solve all of the problems. Before we do that, are there any issues that we should discuss beforehand? The chat seems to be quite empty. So I'm going to go ahead and start by doing problem 1. Yes, there is only one practice exam. There are a lot of other things you can do to prepare for the exam, but there is only one practice exam. Yes. Okay, so now let's start with problem 1. So in problem 1 we have a function which is defined from a formula like this. It goes from R2 to R. And our tasks is to calculate the gradient of f, then the Hessian of f, and then we have to evaluate both the function, the gradient, and the Hessian in the point 0, 0. So let's start by the gradient. We can actually do that down here. At least start the calculation. So here we need to remember what the definition of the gradient is. It's the vector which is formed by writing the two partial derivatives of f as a vector. So we can write it as a column vector like this, or choose any other notation that we might want to look at. Okay, so let's calculate those partial derivatives. So the function is x, e, x, y. So the partial derivative with respect to x, and we calculate that, we need to derive the function as if it only depended on x. And when we do that, it's wise to use the product rule. So first we derive x, then we get a 1. So the resulting term is e to the xy. And then when we derive the exponential term, we get an inner derivative, which is y. So the resulting term is xy e xy. This we can write like this also. The y derivative, same idea. We derive it as if it only depended on y. So then the only thing that we have to derive is the exponential function, and we do that, we get an inner derivative x. So the result is x squared e to the xy. And then the gradient is simply formed by writing the two partial derivatives as components of a vector. What we then get is e to the xy, 1 plus xy, x squared e to the xy. Okay, so that's already the first exercise. Let's continue with the second one. Then we need to calculate the Hessian, and the Hessian is the second derivative of the function. And by definition, that's simply the derivative matrix of this vector field. So let's write that down. So the Hessian matrix is the derivative of the gradient. And let me write down the gradient here again. And then and that matrix is given by the two partial derivatives of the vector field written next to each other. So this formula is only true when we write the gradient as a column vector. Okay, so let's calculate those partial derivatives. When we take the derivative of the vector with respect to x, we need to take the partial derivative for each term separately. So when we derive the upper one, we again use the product rule. So the derivative of the exponential term is e to the xy again times an inner derivative y. And when we derive the parentheses, we get a derivative which is y. So that's that. When we derive this term with respect to x, we first get a 2x here. And then we let that stand and derive this thing with respect to x, then we get y exy. So the total term is x squared y e to the xy. Okay, and then we need to calculate also the second column, then we need to take the y derivative instead. So when we do that up here, we get a derivative x times e to the xy here. And when we derive the parentheses with respect to y, we get an x. And notice that if we rewrite these two terms, we will end up with the same thing. So we get 1x from here and 1x from here, that's the 2x, and x times xy is x squared y. That's a special case of the Clairaut theorem. So that's always a nice thing to do when you calculate these things, to check that these two are equal. If they are not equal, you have made a mistake some way down the calculation. And let's take also the final term of the Hessian matrix. Then we need to take the partial derivative of this function with respect to y, then we get x cubed e to the xy. So yeah, that's the solution to 1b. Okay, and now we need to evaluate f, the gradient of f, and the Hessian of f in 0, 0. That simply amounts to setting x and y equal to 0 in all of the expressions. So let's do that. So f of 0, 0 is 0 times e to the 0 times 0. We simply put x and y equal to 0 everywhere. So the 0 there in front of the e to the 0 makes everything a 0. If we look at the gradient, we need to put 0 in our expression for the gradient. So we get something like this. So we get a 1 here times 1, that's a 1. Down here we get a 0 times a 1, so that's a 1. And if we do it in the Hessian, we get 0 times e to the 0 times 1 plus 0 e to the 0, 0, 1 plus 0 e to the 0 plus 0 times e to the 0. Here we get 2 times 0 times e to the 0 plus 0 times 0 squared e to the 0. And down here we get 0 squared times e to the 0. And we see in all of the terms we have a multiplicative 0. So the end result is that the Hessian in 0, 0 is equal to the 0 matrix. Okay. There is not much to add concerning this exercise, this problem. We simply need to know the definitions of the Hessian and the gradient, and when we do that, we need to perform our calculations. Still, are there questions? Otherwise, we'll move on to problem 2. There does not seem to be any questions, so we continue to exercise problem number 2. In problem number 2, we need to calculate an integral. So we need to integrate the function xy over a triangle with specified corners. So let's sketch that triangle first. So here we have the point 0, 0. Here we have the point 1, 1. And here we have the point 2, 0. So this is a triangle we have to look at. Now, of course, we are going to apply Fubini. So for that, we need our limits. So in order to get them, let's see what these three lines, what equations they have. So this straight line here clearly has the equation y equals 0. As for this thing, it starts in 0, 0, and it has a slope 1. So that needs to be the line y equals x. And this line here starts in 1, 1 and has a negative slope 1. So this line has an equation y equal to 1 minus x minus 1, or also 2 minus x. When we know that, we can start looking at determining limits. So there are two ways to do this, but I think the most straightforward way to solve it is to use x as an outer variable, and then for each x find limits for the y variables. So x goes between 0 and 2, like this. And as for the limits for y, they have different expressions depending on where x is. So in the right part of the triangle, sorry, the left part of the triangle, I think red is better, sorry. In that part of the triangle, y starts down here. That's where y is 0, and it goes up to here, where y is equal to x. However, in the right part of the triangle, so when x is larger than 1, y again starts at 0, but it goes up to this line, which is then 2 minus x instead of x. So once we have these limits, we can write down our iterated integral. So it's actually simplest to divide this into two integrals. One where x goes between 0 and 1. There y goes between 0 and x for each x. Notice that since these are the limits for y, we need to put the y here. And then we get another part which is for the x's between 1 and 2. So this is the blue part of the triangle. And for those values of x, y goes between 0 and 2 minus x. Okay, now would be, so when we have these iterated integrals, it would be okay to simply use a computer algebra system to compute these things and tell us what the answer is. If you make a good reference to that, then everything is okay. So here one could use an external resource to calculate the integrals. Exactly, and when you do that, you need to refer. So either you could put it into MATLAB, then you could provide a screenshot of the MATLAB code you used, of course, or you could use a service like Wolfram Alpha or Symbolab or something like that. Then simply refer to your calculation using a URL. However, in the sake of completeness, I will calculate these two integrals. So let's do that. So when we take the primitive of y, we get y squared halves. That then needs to be evaluated in y equals 0 and y equals x. And then we get the same thing here, but with other limits. Okay, we put in the limits. When y equals 0, that vanishes, so the only thing that remains is the upper limit in both integrals. x2 minus x squared over 2 dx. Now in the solution manual I did a little trick to make this into one integral. That's, I would say, rather a fancy shenanigan than what you really need to do. You can simply also solve this. So we can rewrite the parentheses there as 4 minus 4x plus x squared. So what we then need to solve are these two integrals, plus 1 over 2, 4x minus 4x squared plus x3. Notice that I insert this x into the parentheses. And then what we end up with is the following expressions. And then we get 2x, then we get 1/2 2x squared minus 4x to the third power thirds plus x4 over 4. That we then need to evaluate, and in the sake of time, let me save us of working out all of the fractions here. If you do that, you end up with a third. Okay. So that's the solution of exercise 2. We need to apply for Beanie. We need to another question about what's okay and what's not. So to calculate partial derivatives, you could also put it in Wolfram Alpha and said I use Wolfram Alpha. However, you still need to show me that you know the definitions of what the gradient is or what the derivative of a multidimensional function is and such things. But the calculation, they will not be harder than the ones that we did here. You could also do it with Wolfram Alpha, yes, since all aids are available. However, please refer to the source. It will make it much easier for me to correct the exam. Okay. And what is important here also, which I want to stress, the main part of this exercise is to come up with these limits. So then you need to have some kind of motivations. Drawing a sketch like this surely is enough. You don't need to solve a system of inequalities or write a lot of text, but you at least need to make a sketch like this. If this thing appears out of nowhere, or you simply say I use Wolfram Alpha and the answer is a third, you will surely not get any points. So I would have to sit down and make a more detailed okay, now there's a lot of questions. So I can't say exactly what would give how many points. I would have to sit down and think that through thoroughly in order to get an exact picture of what you need to do and to get certain points. But I mean, an important part is to find these limits from the description. And in that, I want you to either write a sketch or write some kind of text. Then you also need to refer to the tool that you have used in order to get full points. That's important. I would say that the calculations in the actual exam are not harder than the ones we did here. But I wouldn't say that they are per se easier. I could have given this exam as a real exam. It's very close to it's close to the real thing. Okay, that's a good question. So the question is whether we could have used the y integral as a outer integration variable. That's completely possible. Then we need y to go between 0 and 1. However, it gets a bit trickier to determine the limits for the x variable for each y then. It's not impossible. It then needs to go between y and what's that then? X minus 2. It was actually easier than I thought. But that's also a way to do it. Yes, of course. There are often more than one way to get to the solution. And yeah, I mean, let's not make this a long discussion of exactly what you need to do in order to get the right answer. I mean, if you write down a solution which shows me that you have understood the underlying concepts, you will get full points. That's a no-brainer. Okay, then let's go to the next problem. Here we need to calculate a center of mass of a certain region. And the region that we want to look at is the part of the unit disk. So the unit disk is like the interior of the unit circle. So the radius here is 1. And we only want to look at the part which lies inside the region inside the set of vectors where both x and y are larger than or equal to 0. So that means that the region that we want to look at is this thing. Let's call it Q. Yeah, so there is a small the question is what the difference between the center of mass and the center of gravity is. Actually, one of the group solving the group exercises made me aware of this difference. It's really subtle, but the center of gravity is the point. So when you look at an object which has which is not just a point, but really a mass like this, there is really, if there's an object exerting a gravitational force on it, when we calculate the total force, what we then need is to sort of integrate the force over the entire thing. And then if we are really looking at an object which has a which is so large so that the force of gravity is much smaller here than it is here, then that center of gravity is not equal to the center of mass, which is simply the point which is defined through this formula. So 1 over the area or the mass times the integrals of x and y over the region. However, if we are on Earth and not looking at a satellite orbiting the Earth or something like that, we can always assume that the gravity field is homogeneous, so the same everywhere, and then the center of mass is equal to the center of gravity. So the difference is really subtle, and it only becomes relevant when you're looking at large satellites orbiting the Earth far away from the center of the Earth or something like that. Okay, but everything I will ask about is the center of mass as defined in the Book of Stewart. So this thing. And when the density function, so we really need to use the density function here as well, but when there is no density function specified, we are talking about the geometrical center of mass. So then the density function is equal to 1 everywhere. So then the mass is actually equal to the area. So let's write that down first. We know what the area is in this case. It's equal to 1/4 of the area of the unit circle. Sorry, unit disk. This is clearly a quarter circle. So this is pi over 4. We could also calculate this area using an integral, but it's completely fine to use these geometrical facts as well. Okay, so now let's turn to evaluating these two integrals. So let's write them down without so much noise in the background. So now need to evaluate the integral of x over q and the integral of y over q. We will concentrate on the x integral here just in the interest of time. The y integral, the calculation for the y integral looks just the same. So we then need to calculate this thing. And then I guess we could calculate this using a standard application of the theorem of Fabini, but I think it's much easier to go over to polar coordinates. So since this radius is 1, r clearly goes between 0 and 1, and down here theta is 0, and up here this angle is right, theta is pi halves. So the new limits are clearly that r goes between 0 and 1, and theta goes between 0 and pi halves. X turns into r cosine theta. And when going over to polar coordinates, we mustn't forget the Jacobian or functional determinant. That's an extra r here. So another way to express this is that the x dy is equal to r dr d theta. And now I need to write the theta dr here because the limits for the theta variables are the innermost integrals. So the reason why the density is 1 is that we are speaking about the geometrical center of mass, simply because there is no density specified in the task. If questions about this arise in the exam, I will be there all of the time. So if you don't see the density function or are unsure what the density function is, just try to get to me to ask the question. Maybe I can't answer it because maybe there is some information in the task which you should use to obtain the density, but it might also be that it's simply equal to 1. Then simply ask me and I will tell you. That's no problem. It's better to ask the question than to miss points because of such things. So another question, why is the area pi over 4? So the area of the unit circle is pi. Pi times the radius squared, not 2 pi r. Not 2 pi. 2 pi is the circumference of the unit circle. Yeah. How do I decide whether to integrate with respect to the theta or the r first? In this case, when the limits do not depend on each other, I can choose to do whatever I want first. And in this special case, there is really nothing making it easier in any particular direction. However, often when we do these things, we need to make a full revelation around the theta integral, because simply a lot of simple solids that you can write down have rotational symmetry, and then theta needs to go around the entire thing. And then if there's a so to say naked cosine term like this, we know that when we integrate that vanishes. So that can simplify calculations. That's why I usually do the theta integral first, but you can really do it any way you want. That's actually a part of the theorem of Fubini. It says that when you're integrating over a square, over a rectangle like this, which we are doing in the r theta domain, we can change these two integrals and not change the value of the integral, as long as we're of course also changing the position of theta and r in the at the end of the integral. Okay. When we've come this far, we can again use a computer algebra system, of course, but let's simply calculate the integral instead. So a primitive of cosine theta is sine theta. Let me just finish this integral, then I'll come to the question. So when we evaluate here, we get a 1. And then when we calculate the r integral, we get r 3/3. Evaluating that, we get a third. So the question is if you have to refer to the theorem of Fubini in these kinds of problems, or is it obvious? I mean, it doesn't hurt. I mean, if you know that you're applying the theorem of Fubini, it surely does not hurt to write down that you're doing it. It makes it easier for a reader to follow the solution. However, if we're speaking about giving points or not, I think it would be too. I mean, I think it would be unnecessarily meticulous to withdraw points for that. But I mean, it doesn't hurt to write more. if you know that what you're writing is correct, it makes it easier to follow. So that's my answer to that question. If you do some calculations by hand, but then use software to check your calculation, no, surely not. I mean, if you just check the calculations, no. I mean, what you would then write is that, well, and when I ended the calculation, I checked that this was correct using software. No, you don't need to do that. So I mean, the calculations are as hard as these calculations on the real exam. So the question is if you choose to don't use a computer algebra system, the calculations are not that hard. Of course, it takes time to write this down, but for this particular example, you could argue that it actually takes more time to open up a window in Wolfram Alpha, put down all of these things with the correct limits, and then write down the final answer. But I mean, all aids are available, so I completely understand if you use a service like this. I mean, everyone does mistakes, the computer does not. So in that sense, it's more secure to let the computer check the calculation. However, when you do that, I need you to refer what service you are using in order to make it easy. That makes it easier for me to determine what's happening in the solution. Okay. Let's end this example. So I'm not going to do that now, but when we do the y integral, we end up again with a third. So the center of mass then finally is 1 over the area, that was pi fourth, times 1/3, 1/3. And that's 4 over 3 pi, 4 over 3 pi. So that's the center of mass. Okay. More questions about this particular problem? Does not seem so. Then let's continue with problem number 4. I mean, I could argue using the fact that this body is symmetric around the line x equals y. So if we change the roles of x and y, we end up with the same body, and then the integrals will be the same. That would be an argument more that if you do the calculation, you get 1/3. Exactly. Exactly. Since the shape is symmetric. Exactly. And also, if we would have a density, we would have to perform all of these calculations using the density function, both here and when we calculate the area, so to speak. So then we would have to divide by the mass. Yes. Yeah. So, I mean, we could either assume that it's constant or say that it's equal to 1. And we could also say that it's equal to 1 mass unit per area unit. So we would then redefine the mass unit and the area unit to make it 1. Yes. As any lecture, this lecture will be also uploaded to YouTube. Yes. Okay. Let's push on to problem number 4. And here we need to solve an optimization problem. So we need to optimize x. We need to find a maximum of x to the ey. So notice that we need to find the maximum and not the minimum. subject to a constraint. So in the A problem, we need to find the solution. So A. And what we have here is, of course, an optimization problem under a constraint. And I've written it in the standard form so that the function g is equal to 0. You don't need to do that, but for those of you using the Lagrangian formalism, you need to do that in order to get the things correct. Okay, so this is the g function. And this is the f function. So this is a constrained optimization problem. Then Lagrange is the way to go. We know that as long as nabla g is not equal to the 0 vector, there must be nabla f is equal to lambda nabla g for some lambda in R in the point where max occurs. And observe that the problem text actually gave us that a maximum exists. So we don't need to worry about that here. That was also explicitly mentioned. Okay, so then let's first real quick check that the gradient does not vanish anywhere on the set of feasible points, sorry. So when we calculate the gradient of x plus y minus 1, we get a 1 for the x derivative and a 1 for the y derivative. So that's our gradient. And that constant vector is surely never equal to the 0 vector. So the Lagrange condition actually applies. It might seem that it's nitpicky to actually check this, but if the gradient is 0 in a point, we need to take extra care about that point, because that would then be a point in the set of feasible points where there is a cusp. And in such points, the Lagrange condition does not need to be true is not necessarily true even if we have a local maximum or minimum there. So pay some attention to that. It's not just checking it for checking's sake. There might be problems when the gradient is 0 somewhere. Okay, but once we have checked that, we know that in the point where the maximum occurs, we have that the gradient of f, so f was x ey, so the gradient is ey x ey. Partial derivative with respect to x, then the x turns into 1, and partial derivative with respect to y, then the e to the y still stays an e to the y. That should be equal to some lambda times 1, 1. And this can only be true when e to the y is equal to lambda is equal to x times e to the y. This is exactly the case when e to the y minus x times e to the y, so e to the y 1 minus x is equal to 0. This is only true when x is equal to 1. e to the y cannot be 0. So that means that in the point where the maximum will occur, the x coordinate must be equal to 1. And then we can find out the second coordinate from our constraint. So x equals to 1. If we use the fact that x plus y is equal to 1, that shows us that the y coordinate must be 0. So the maximum must occur in the point 1, 0. Question about that calculation. There does not seem to be any. I hope that the idea is clear. We have a maximum under constraint, then Lagrange is the way to go. There are other methods, but that's probably in most cases the easiest one. Then we first need to check if the gradient vanishes anywhere. That would be a problematic point. And when we have that, we can try to see where the Lagrange criterion holds. Okay, let's also do the B task before we take a short break, maybe just 5 minutes. In the B task is about the question if the minimization problem has a solution. So does this problem, minimum of e to the x times e to the y, subject to x plus y is equal to 1, have a solution? Okay, and now we have to think a bit creatively. So the set of points that we have at our disposal is the line x plus y equals 1. So that's this line. Notice that if we move on the line in this direction, we would make y become infinitely large. So that means that e to the y becomes infinitely large. And we would make x become arbitrarily negative. So x would go towards minus infinity. So that means that x goes towards minus infinity. Minus infinity times infinity is minus infinity. That hand-wavy argument shows us that we can make the function arbitrarily small on the set of feasible points, and so by arbitrarily small I mean arbitrarily negative, and therefore there cannot be a minimum on the set. So a formal way to write down what I just said is something like this. So we can notice that all of the points of the form t1 minus t are feasible. So they obey the constraint. Then if we evaluate f in such points, we get t to the e to the 1 minus t. And then if we let t go to minus infinity, this exactly corresponds to following the line up like that. We would make t to the t times e to the minus t go towards minus infinity times e to the 1 plus infinity, which is then equal to minus infinity. And the fact then that we can find points on the line for which, so that when we let the parameter t go to minus infinity, that f goes to minus infinity, shows us that there are points on this line where f is smaller than any given number. So let me write that down. We can make f arbitrarily negative on set of feasible points, and that means that there cannot be a minimum. And yeah, that's the solution. Question from the set: why do I use t? To some extent, I'm parameterizing the set here. So I'm giving a parameterization of the set of the feasible points, and then we often use t as the parameterization variable. We could, of course, use x, or or drawn a small elephant instead of using t. But the reason I did use t was that I kind of parameterized the line. I hope that's a good explanation. So a point here which I want to make is that this example shows us that it's relevant to think about whether points, whether minima exist. So if we would just start calculating using the Lagrange criterion to find the point where the minimum occurs, we would find the same point as in the previous calculation. So that means that we would find a point which is not the minimum. So that's why you need to, before you start calculating, at least shortly think about whether there exists a minimum. If there does not exist a minimum, you can't find it using any method. Okay, more questions or comments concerning this problem in general, or this problem is specifically, or optimization problems in general? Yes, so on the solution sheet, I sort of used what I just said as an argument. So if there would be a minimum, that minimum would have to occur in a point where the Lagrange criterion is true. And in the A task, we show that the only point where the Lagrange criterion is true is the point 1, 0. So if there would be a minimum, it would need to be attained in the same point as the maximum was attained. So that would mean that the function is constant, which surely is not. So that's an alternative way to do it. I mean, it could be that, I mean, there are, so if the function is constant, any point is a maximum and a minimum, but that's also the only case where any point is both a maximum and a minimum at the same time. Okay, we're running out. We're a bit behind schedule here, but I'm still going to take a 5-minute break so that you can at least have some pause during this lecture. So we'll continue again in 5 minutes with the final 4 exercises. Problem 5. So here we need to first read a bit. So we have a circle and we know its center. The center is given by the point 0, 1. But we do not know its radius. So what we do then is that we determine one more point on the circle. Let's call that point xy. Once we've done that, it's of course a short job to calculate the radius of the circle. The radius is then given by the difference, the norm of the difference between the two vectors xy and 0, 1. So using Pythagoras, that's x squared plus y minus 1 squared. Okay, now we have done that and we have determined this point to be 1, 1. So this is actually not what's in the sketch here, but that's what the measurement says that we have. However, both of these two coordinates are subject to errors, and these are not larger than 0.1 length units in each coordinate. So the actual value let's call it x tilde y tilde, fulfills that the difference between x and 1 is less than 0.1, and the difference between y and 1 is less than 0.1. And now our task is to use the Schrankensatz to give an estimate of the area of the circle with error bounds. So the Schrankensatz is of course used to determine the error bounds. There is actually there's something wrong with the statement here. So this should be the radius of the circle. Okay, I'll change that afterwards. Okay, anyhow, let's try to do this. So what does the Schrankensatz say? Well, the Schrankensatz says that we can determine the difference between r x tilde y tilde and 1, 1, or we can give a bound for it by this formula. So these mx and my's, those are the maximums of the partial derivative of the function with respect to x and y. Both in modulus. And we take the maximum over all possible values. So x minus, sorry. Here we need to let x go between all values whose absolute value, whose absolute difference to 1 is smaller than or equal to 0.1. Okay. So then we need to determine these two numbers, and in order to do that, we need to take the partial derivatives of our function. So rx comma y is equal to square of x squared plus y minus 1 squared. So the partial derivative with respect to x is outer derivative 1 over 2 times the thing in the square root, sorry, times the inner derivative, which is 2x. So we simply get this. Yes, I mean, so the question is if it's acceptable to leave out these bounds. I mean, formally it's then not correct. Then the max would refer to the maximum over all of R2, and then, I mean, the bound would be correct, but then we would get infinity everywhere. So what we did afterwards would not be correct. However, from the context, I would say that it's clear that we only take the maximum over that region. So that would be borderline, but it would be okay. Okay. In any case, the same calculation for the y-coordinate leaves us with this partial derivatives. Okay, now we need to use these expressions to determine values for mx and my. So let's concentrate on mx. So, and now let's leave out the bounds to save some time. And the thing that we need to bound is x over the square root, x squared plus y minus 1 squared. And we need to take the absolute value. Okay. Now, of course, the best error bound we would get by calculating this maximum. However, that would in itself be an extremely long calculation. It would be much harder than the optimization problem that we already solved. So notice that we want to determine error bound. So it's enough to estimate this maximum upwards. And it's okay to do that quite liberally. So the strategy here is to determine the largest possible value that the denominator can have. And the smallest possible value of, and let me use colors instead, the denominator. And we can do that independently of each other. We're only determining a bound, we're actually not determining the exact maximum. Okay, so how large can x be? Well, x goes between 0.9 and 1.1, so the largest possible value is 1.1. So that was no problem. How small can we make the expression inside the square root? Well, again, x squared goes between 0.9 and 1. So the smallest possible value there is 0.9. And how small can we make y minus 1 squared? Well, y goes between 0.9 and 1.1 also. So if we choose y equal to 1, we get the smallest value. So we can actually make that square be a 0 squared. So a bound for mx is 1.1 over 0.9. Observe that the square root and the square cancel each other out here. Is this step clear? Because I think this can be a bit confusing at first. Notice importantly that the value that we need to insert to get a bound does not need to be either the left or the right boundary of the interval for y. It may be that we need to insert something in the middle. Okay. If we do the exact same consideration for my, we get a bound 0.1 over 0.9. So the only difference is then that we have y minus 1 up here, and that's as large as possible when y is equal to 0.9 or 1.9. Yes, so the question is, could we pick 0.9 in y? Yes, but that would not give us a particularly good bound. because then we would divide. Wait. So sorry. We can't pick y equals to 0.9 down here. Why? Because then we would divide by something larger than what we have now. So that would not be a valid inequality. If we choose x equal to 0.9 and y equals to 0.9, we would get, and y equals 1, we would get a smaller value than we choose it like this. So it's not correct to choose y equal to 0.9 on here. We would not get an inequality. Exactly. Okay, but when we have these bounds, we get a bound for the error. So we get a 1.1 from here. And a 0.1 from here. And notice that x minus 1 is smaller than or equal to 0.1, and y tilde minus 1 is smaller than or equal to 0.1. So the final thing that we end up with, and that fits here, is 12/90ths. So in the end, we then get that the value for the radius of the circle is closer for the value that we measure than 12/90ths. And this thing is equal to 1. That we can obtain by simply inserting 1 into our expression. So the final answer is that the radius of the circle is equal to 1 plus minus some error, which is not larger than 12/90ths. Okay. Questions, comments about the Schrankensatz or these specific calculations, of course. If not, we will move on to the sixth exercise. I think one main takeaway here is to notice that when we determine our bounds for mx and my, we need to be careful. We can't just, for instance, put in the largest value for x tilde to get an upper bound. We need to check how large and small each of the components in the expression can be made. Okay, then let's continue with exercise number 6. Here we move on to line integrals and conservative vector fields. So we have a curve here. It's a quite weird curve. The parameterization looks kind of spurious. And we have a vector field which looks a lot simpler. So the first thing we should do is to prove that the vector field is conservative. And we should also calculate a potential for the vector field. So let's do that. Then we'll worry about B later. Then we need to calculate line integrals, but let's start with A. Okay, so the vector field looks like this. 0, 0, z cosine z plus sine z. And we need to determine if it's conservative or not. So the definition of a vector field being conservative is that there exists a function g so that v is the gradient of g. So since we need to calculate that potential, we might as well just make an ansatz for G. So say that there is, just assume that there is a G, and then try to calculate it using the definition of a potential. So sorry. Then the partial derivative of G with respect to X needs to be 0. So that's this 0. The partial derivative with respect to Y also needs to be 0. And the partial derivative with respect to Z needs to be equal to Z cosine Z plus sine Z. Okay, and now we need to find a solution to this system of differential equations. That's a lot simpler than than you might think. We simply need to successively integrate these three differential equations. If we at some point end up with a contradiction, our assumption that there exists a G is false, and then we cannot have a potential. This will not happen in this case, but you could always just make an ansatz and try and see if there's potential. If you end up with a contradiction, that means that there cannot be a potential. Yes, the definition of V being conservative is exactly that it has a potential. So if we find a potential, it surely is conservative. Okay, so now let's solve this, and let's do it in a very streamlined fashion. These two equations mean that G is independent of X and independent of Y. It cannot depend on X and it cannot depend on Y, because the two partial derivatives with respect to X and Y are both 0. So G is really a function which only depends on Z. And that we can then use in the final equation. So let's do this really formally correct. So G of X, Y, Z is equal to h of C for some h. And this h is the primitive function of the derivative of G with respect to Z. So that's Z cosine Z plus sine Z. This primitive function calculation we can solve using partial integration. So if we integrate cosine, we get sine. And then we need to compensate by taking sine Z away. That's the result when we derive this expression, when we derive the Z then. The sine Z from there stays. So what we get is then that Z must be equal to Z sine Z plus some constant. Okay, why was the GGX equal to 0? Because V being equal to the gradient of G exactly means this. The gradient of G is the vector with the three components, the g dx, the g dy, and the g dz. That being equal to the vector field V everywhere means that the g dx is 0, the g dy is 0, and the g dz is equal to Z cosine Z plus sine Z. So that's the reason why the g dz is equal to Z cosine Z plus sine Z. Okay, and if we take the derivative of this thing, we see that we get the correct thing. So a potential for our vector field is given to us by z sine z. We could have chosen any other value for the constant, but I think 0 is a nice value. Now a few of you are probably asking yourself, but shouldn't you calculate the curl when you're checking if a vector field is conservative? Or you should check the integrability criteria. I mean, you could do that. Since V is a vector field which is defined everywhere, the curl being equal to 0 is sufficient for a potential existing, so the vector field being conservative. However, since we in any case need to calculate a potential in this case, that would be unnecessary work. So we would still need to do this calculation in order to get a potential. Also, remember that the curl criterion is only true on simply connected domains. So watch out for that if you're using the curl criterion. Okay. If there are no comments about calculating potentials in general, I will move on to the B task. There does not seem to be. Please write them if they are still there. I'll continue with the B, start writing up B in the meantime. So in the B task, we need to show that the line integral of all of these vector fields along all of the curves are equal. Now, one way to do this would, of course, be to calculate these line integrals using the definition. Okay, a question concerning the other point. So in this, so the question is if you would get some points by showing that V is conservative by using the curl criterion. I mean, you would get partial points, but you would not get all of the points because in the problem text, it specifically states that you need to calculate the potential. But you would surely get partial points for doing that, for only checking that a potential exists. Of course. And I mean, watch out. Sometimes the question is only to show that there is a potential. So then you don't need to calculate it. So you need to watch out. Okay. Where was I? So we could do this using definition. However, since we have a potential, we know that we can use it to calculate the line integrals. So V is nabla G, so we can apply the fundamental theorem for line integrals, which says that the value of the line integral is given by the difference in potential value between the start point and the end point of the curves. So why are these now equal? Well, remember that G only depended on the Z variable. This means that the value of this difference only depends on the value for the Z components of the start point and the end point. So let's check what they are. So if we put 1 into our formula in the parameterization, we get cosine pi alpha, sine pi alpha, 1 plus 2 sine squared 1. And for the starting point, we get 0, 0, 0. So even though the start point is independent of alpha, but the end point is not independent of alpha. However, the z coordinate is. So that means that the value of our line integral, which only depends on these two things, are independent of alpha, and that's what we need to show. Yes, of course. So this is the fundamental theorem of line integrals. When v has a potential, we can calculate the line integral along a curve so this is not what gamma alpha looks like, but I think you get the point. By comparing the value of the potential in the start point and the end point. That's one thing that potential can be used for. So that's the meaning of this formula. Is that then clear? Perfect. Okay, and I'm actually going to just write a square here. Because we have written everything, I have written everything that I would write to explain why this is independent of alpha. So, I mean, this is one step above the standard the standard discussion for these type of things. So this theorem in particular shows you that if you have two curves which have the same start and end points, we would get the same value for the line integral. This is only true for conservative vector fields. In this example, we do not have curves which share the same endpoint and the start point and end point. The x and y components of the endpoint depend very much on alpha. However, the potential only depends on the z coordinate, so we only need to look at the z coordinate. So we really need to know the fundamental theorem of line integrals to solve this exercise. Exactly. This theorem only holds true for conservative vector fields. I mean, it would be pointless to write it down if v was not conservative, because then we wouldn't have a potential. Exactly. Everything here depends very much on v being conservative. Okay. Then let's go to problem 7, the first one of the more problem-based / theory-heavy problems. And I know that I'm running short on time here, but I'm going to oh no, we have at least 15 more minutes, so we're okay. If there are, so then let's take the opportunity to see if there are more comments about conservative vector fields and or the calculation, that specific calculation. Okay. I'm going to bring up the exercise problem. I'm going to bring up problem 7, and let's start trying to solve it. So what do we have here? We have a function which is defined in a very special way. So what it does is that when it gets a point xy, it first checks if it's on the curve y is equal to x squared. In such point, it then gives us the value of the y coordinates. So on the red line, f of x, y is equal to y. However, if we're not on that line, it simply gives us 0. And now we need to answer 2 questions about this function in this problem. So the first problem we need to look at is if f is partially differentiable in 0, 0. And what we now cannot do is to partially differentiate, and that's also true. I can already say that for b. We cannot simply look at both of these 2 expressions by themselves. So as functions, as the function always equal to y and the function always equal to 0, and say that those 2 parts are partially differentiable or continuous, and conclude that the entirety is continuous. Because when you look at continuity and such things, you need to see what happens when you go away from the point in any direction. You can't only look at what's happened when you move along this curve or when you're moving in the set in the complement of the curve. You need to look also at things which goes through both cases. So we cannot separate the 2 cases for the function and look at them separately. So what we instead need to do here for a is to check if it's partially differentiable in 0, 0. And the easiest way to do that is actually to use the definition. So for instance, the definition of the partial derivative with respect to x, that's not usually how we think about these things, but it is actually defined by a limit. It's defined by the standard derivative limit, but we only change the value of the x coordinate, like this. Okay, and now let's see what this limit is equal to. Notice that when we're in a point t0, we're on the x-axis like this. Those are points in which f is equal to 0. So this means that ft, 0 is equal to 0 for all values of t. In fact, also for t equal to 0, since in that point we need to check this branch of the function, but y is equal to 0 in the point 0, 0. So that means that both these 2 expressions are equal to 0. No, the function is not equal to the function y. The function fxy is equal to y, I should maybe use gxy is equal to y, would give us the value of the y coordinate of the point in any point in R2. F only gives us the value y in the points on the parabola. So, I mean, this is a weirdly defined function, but it's a well-defined function. Okay. Then 0 minus 0 is 0. So this fraction is actually equal to 0 all the time. And now I need to change slide. And the limit of 0 when t goes to 0 is 0. So by the exact same argument, we can also prove that the limit we need to calculate in order to calculate the y derivative is 0. So again, if we look at a point of this form, we're also not on the parabola, so that means that f is equal to 0 for all such points, and then we get 0 minus 0 again, and that's 0, so the limit is 0. So even if the function looks, even this weird function, even if the function looks weird, I should say, it is very much partially differentiable, and the partial derivatives are equal to 0. So going back to the definition of the partial derivatives, we get that. Okay. There does not seem to be any comments or questions, so we're going to move on to the B task. Oh, there is. It's always okay to use the definition for showing differentiability. However, notice all of these subtleties when it comes to differentiability versus partial differentiability. That we could speak about for half an hour, but remember that a function being partially differentiable does not necessarily mean that it is differentiable. That's something which is nice to look at. Okay, so as for the B problem, we need to check if it's continuous in 0, 0. And then, by the definition, that's exactly the same as asking if the limit of fxy as xy goes to 0, 0 is equal to the value of f in 0, 0, which in this case is 0. So, okay, how would we go about to solve this problem? Well, let's look at the formula for f. So the definition is a bit wonky, but it is surely true that fxy does not exceed the value of y. I mean, either it's 0 and then it's smaller than anything, or it's equal to y and then it's of course also smaller than or equal to the absolute value of y. And the absolute value of f is actually the difference of x comma y to 0. So, I mean, this is certainly true when y is not equal to x squared, and also when y is equal to x squared. The absolute value of y is smaller than or equal to the absolute value of y. Okay, but the absolute value of y surely goes to 0 when xy goes to 0. We could prove that using the sequence criterion if we wanted to, but that's a well-known fact that when a vector goes to 0, 0, both of its components go to 0, 0. Or, I mean, if it goes to any other vector a, b, each corresponding component goes to a and b. I think you get what I mean. So in any case, the squeeze theorem then gives us the claim. Fxy is smaller than or equal to something which goes to 0 when xy goes to 0. The squeeze theorem then implies that the limit of fxy when xy goes to 0. I'm sorry that this is so cluttered, but I think it's better to stay on the slide. Sorry. That shows us that fxy is equal, the limit of fxy is equal to 0, and that's equal to the value in 0, 0. So that is by definition continuity then. So yes, it is continuous. So in order to solve this exercise, we need to know our definition of continuity. We also need to know our squeeze theorem and how to apply that. Okay, let's do the last problem, number 8. So here there's a lot going on. Let's check it one thing at a time. So we have a vector field, which is defined in a certain way. And then the very first question is to calculate the value of dy1, so the partial derivative of the first component with respect to y minus the second component with respect to x. That we can simply do. I will not invest time writing down the actual calculation here. You could also do it using a computer algebra system. The answer is 0. Okay, I mean, calculations can be made on computer. That part of the exercise is more or less a tip to see what you will need in the following exercises. So in B, we then need to evaluate the line integral of V along the unit circle. And it should be traversed in a counterclockwise fashion like this. Now, what one could be tempted to do is to apply the Green theorem. So the Green theorem would then be to take those two partial derivatives, take exactly that expression. We need to put a minus sign on it, and then integrate that over the unit disk and get a 0. However, we can't do that, because if we look at the formula for the vector field real quick, we see that we divide by x squared plus y squared. That means that the vector field is not defined in 0, 0. This is actually also explicitly pointed out here in the notation. So that means that Green cannot be applied. So we need to calculate the line integral by hand. And I'm actually going to skip the main part of the calculations here as well. So what we need to do is to parameterize the unit circle. The canonical way to do that is to use cosine theta sine theta. Theta goes between 0 and 2 pi. And then we need to put that into the vector field, calculate the derivative, getting the dot product. I'm going to skip that simply because the clock is already 10 o'clock. You would need to write down the beats of these calculations at least in the real exam. To calculate certain derivatives or calculate the resulting integral, you could of course use a computer, but I need you to show that you know the definition of the line integral. Okay, in the end, however, we would get to the conclusion that the integral is equal to 2 pi. So notice that if we would were to apply the Green theorem in the unit disk, we would get the wrong answer. The derivative is equal to, the integral is equal to 2 pi, not equal to 0. Okay. Let's also do the C task. So in C, we have our circle, and we have a triangle which encompasses the circle like this. And then the question is what the value of the line integral along the border of the triangle is. And here it's wise to apply Green. If we call the area in between the circle and the triangle for, say, f, the Green theorem tells us that the integral over dv 1 dy minus dv2 dx, dv2 dx minus dv1 dy. If we integrate that expression over f, we get the same thing as the line integral of v along the boundary of f. That's then equal to 0 because of the A task. Because there we calculated that the thing that's inside the Green integral here is exactly equal to 0. Okay, now however, what is now the value of this line integral? Well, this line integral has two parts. We for one have the line integral along the triangle, and the correct orientation for that curve is counterclockwise like this. So that's the thing that we need to evaluate. And then we need to also take the line integral part of the inner circle into account, but there we need to go through the circle in a different direction. Only in this way the area f is on the left of us all the time. So by A I mean task A. In task A we okay. Now I get it. So in that task we evaluated dv1 dy minus d1 dx, right? So minus this thing. And if something is 0, then minus the thing is also 0. Right? Okay. Perfect. And now the important part here is that so what things are equal to each other? We have a question in the chat. So you mean this? So do you mean this integral and this integral, this integral and this line integral? Those two are equal because of the Green theorem. If we apply the Green theorem to the blue area, this is exactly what it says. Now, however, when we calculate this boundary integral, we can take the derivative on t counterclockwise, but we need the integral along the unit circle to be counterclockwise. So that's exactly the negative of what we just calculated. So the minus here is due to a change of orientation. So notice that in the last task we used cosine theta, sine theta, then we went through the circle in this fashion. However, when we do that, the area F is not on the right of us. It's not on the left of us, it's on the right of us. So that would be the wrong direction. We need to change the orientation, and that's why we get a minus sign here. Okay, it might be true that I've written something else in the solution manual, but I hope not, because what we're doing here is correct. So what you may be referring to is the placement of these two. That would then be a typo. Yes. Anyhow, we know that this thing is 2 pi, so that the thing that we look for, minus 2 pi is equal to 0, means that the sought for integral is equal to the thing we calculated in B, and that's 2 pi. Very good point. So we have a question which I really wanted to do, which I really wanted to discuss earlier, but yeah. So the question is, why can we use green? Why can we suddenly use green now? We couldn't use it in the B task. Well, the point where V is not defined is the 0, 0 dot. If we would apply green in B, we would need to apply it on the unit disk. That point contains the point 0, 0. So then green is not true. However, in the C task, we're applying the green theorem of the space in between the two curves. 0, 0 is not a point in that domain. So that's why green is okay there. Excellent question. That's a very important point. As long as the vector field is defined everywhere in the domain in which we apply green, everything is green. I hope that's true. Okay, and about the orientation, there are several ways to do that, but my favorite thing is the following. So for green, it's actually simpler than for Stokes. Then we simply need to imagine that when we go along the curve and look forwards in the direction that we're traversing the curve, we need to have the area on our left. When we're applying it in 3D for Stokes, we also need to make sure that the normal is pointing upwards when we look to our left. I think that's one way to explain it, at least. There are other ways to do it with looking at your fingers, but that's my favorite. And in the plane, I think it's also the most convenient one. Of course. So I'm very aware of that the clock is 10 past 10. So we've gone through all of the exercises now. So we will continue discussing, and that will be on YouTube. But if you have to leave for another lecture, I thank you very much for the entire course. It has been a lot of fun. And I wish you the very best of luck in preparing for the exam and also writing the exam. I really hope that we can achieve great things together in the exam. And we have also prepared ourselves good for the exam. So I think I hope and I think that the results will be good. Okay. So now to the circle and the triangle. So notice that when we go through the triangle in this fashion, the area F is on our left all of the time. However, if we would go around the circle in the same fashion, F would be on the right. It would not be on the left. So that's why we need to go through it the other direction. When we do that and look to our left, the area is there. I hope that's clear. So old exams, I've chosen not to do that because the exam our exam will look a bit different compared to old exams. So that's why it's unwise to rely on old exams to see what the exam that will be posted on Tuesday will look like. So again, the circle and the triangle. Let me change slide here. So if we would, so let's zoom in only on the circle. If we would traverse it in a counterclockwise fashion, then when we stand here and move forward, the area F is on our right. Right? But it shouldn't be. It should be on our left. So that's why we need to traverse it in the other direction. Perfect. Okay, so then let's round off here. I will log into Discord ASAP as soon as I've switched places here. So if there are any questions, we can also discuss them in the Discord. So thank you very much for the attention.